so section 10.4 is on exponential and logarithmic equations and inequalities. So you guys struggled through 10.3. You switched forms. You didn't like it. There are going to be some other ways to do this instead of switching forms every single time. Okay, so an exponential equation is an equation containing one or more expressions that have a variable as an exponent. In order to solve an exponential equation, you can do one of three things. If you can get it to look like b of x equals b of y, then you can say that x is equal to y. So for example, if I have 2 to the 5 equals 2 to the x plus 2, what could I say?
5 equals x plus 2.
Exactly, 5 equals x plus 2. So that would be ideal if we could do that. A second way, it says take the log of both sides in order to drop the exponents. Or 3, when in doubt, always just try to switch forms. So you can switch from exponential form to logarithmic form. Okay, that's what we've been doing on the last couple of homeworks. Okay, so number 1, it says we have 9 to the 8 minus x equals 27 to the x minus 3. Can I write 9 and 27 with the same base somehow? Yeah, 9 is 3 squared, and 27 can be 3 cubed, right? So I'm going to do that. So I'm going to have 3 squared is raised to the 8 minus x, and I'm going to have equals 3 cubed raised to the x minus 3. If you can do that, always go that route. It's much easier than doing logarithms. Okay, so I'm going to multiply here for my powers. So I'm going to have 3 times 16 minus 2x equals 3 times 3x minus 9. Notice how I'm distributing the 3 in. So I'm to that point. I have 3 raised to a power equals 3 raised to a completely different power. Right? Those powers have to be the same thing. So I'm going to have 16 minus 2x has to be equal to 3x minus 9. And I solve. So I add the 2x over, so I get 5x. I add my 9 to the other side, I get 25. So I end up with x is equal to 5. And you can check. If you do 9 to the 3, it is the same as 27 to the 2. Okay, but we don't always have things that we can get to be the same base. So do you see the problem on the next one? Like 4 can be 2 raised to something, but I don't know what 5 is. It's not 2 raised to something, right? So in this case, I do another method. So I'm going to do a couple different ways. So the first way that I'm going to try is I'm going to just switch forms, which is what you've been doing. So when I switch forms, if I have 4 to the x minus 1 equals 5, I just get log base 4 of 5 equals x minus 1. Do you all see it? You can check. 4 raised to the other side equals the 5, right? 4 to the x minus 1 equals 5. It works. So then I have log base 4 of 5. And if you're lucky like Yaya, you have log base on your calculator. Some of you guys don't have log base, though. So you have to do log of 5 over log of 4. Personally, I think it's faster than going through the math, like hitting math and arrowing down to log base anyway. Yeah, Alex? Yeah, that's true. So what I'm going to do is I'm going to add the 1 over, so I'm going to have log of 5 over log of 4 plus 1 equals x. This would be what I call exact form. Okay, you could also have, don't write this, but you could have log base 4 of 5 plus 1. That might be exact form as well. And some teachers make you leave it in that form. The reason is because a lot of times in college you don't even get to use a calculator. Oh, all of your tests are non-calculator. Isn't it nice that I've been preparing you all year and giving you non-calculator exams along with calculator exams? So terrible. Now I personally prefer decimal. I like to see the decimal answer. Okay, so what I'm going to have you do is do log of 5 divided by log of 4. You get 1.16096 blah 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 plus 1. So you get 2.161. And I'm going to have you round to 3 decimal places. I don't know why that's highlighted there. All right, so that's going to be our answer. So that's the first way you can do this problem. The second way. The whole reason we invented logarithms is so that we can drop exponents that have x's in them. Okay, remember we said if we take the log of both sides, right, if I do the log of both sides, now I have an x minus 1 as a power. And as long as I have a log, I can pull any exponents to the front. So what happens is you get x minus 1 times log of 4 equals log of 5. Does that make sense? We divide our log of 4 over, so I get log of 5 over log of 4 equals x minus 1, and I'm already to the same thing that I had right there. So I'm good. And you end up getting exactly the same answer. So you get x equals 2.161. Does that make sense? Just taking the log of both sides? Yes.
So it doesn't matter which one you use.
It doesn't matter, whatever way you want to do. So if you are not comfortable with switching to log form, like sometimes that's the harder way, right? You guys have trouble. You have to like think about switching to log form. Then just do this. Take the log of both sides. When I taught at IU, what I always told my students is to, I was like, oh yeah, just remember our cancellation formulas. Do you guys remember how like if you have log base 7 of 7 to the 5, it's like the 5 goes to the front, and then the log base 7 of 7 just cancels, so you end up getting 5. So what I tell all my students is that when they had something like number 3, 7 to the negative x equals 21, I just said, oh, well, if you just do log base 7 on both sides, then you're good, because this becomes negative x, right? Like this goes to the front, it cancels. Do you see what I'm saying? You don't have to write this, just kind of pay attention. So you get negative x equals log base 7 of 21, which is log of 21 over log of 7, and they were good. They would get the answer. That's perfectly fine, except I didn't write the midterm and final. I wrote all of the tests that we did between those two things, but I did not write the midterm and final, and the person who did put a question like 4 to the x minus 1 equals 5 to the 2x plus 3. And my students totally freaked out. They were like, wait, do I do a log base 4? Or do I do a log base 5? Which one do I pick? And it doesn't matter. It doesn't matter what log you do. I could have done log base 200. It doesn't matter. It's still, the whole reason we do a log is so we can pull the power to the front. So since then, I've always just taught just to take a regular log, or even to take a natural log, which we'll learn about the next section. Does that kind of make sense? So just take a regular log. So like on this example, you could switch forms. Do you guys like the method where you do just the log in front, so you don't have to think about it? So let's just take our regular log. We're going to pull the negative x to the front. We're going to get negative x times log of 7 equals log of 21. We're going to divide, so log of 21 over log of 7 equals negative x. So I'm going to go ahead and find that. So I get x equals log of 21 divided by log of 7. And try this along with me. So you get negative 1.565 when I divide my negative over. Does that make sense? The reason I'm saying do it along with me is because everybody always forgets to end this parenthesis around the 21 before they divide by the log of 7. Okay, so you want to end that parenthesis. Okay, I often also get the question, why can you not just cancel the logs? Was anybody thinking that you could do that and it would just be 3? You can't cancel the logs. You guys all understand that? It's kind of like sine. Like when you guys were doing geometry and you had like sine of 45 divided by sine of 30, right? You can't just get rid of the signs. It goes with the 45. It goes with the 30. This is called the argument. Same thing here. It goes with the log. You can't get rid of it. Okay. So anyway, so next one. You guys want to try number 4? Actually, maybe I should. We don't have much time. So we're going to do log of both sides. So I'm going to have log of 2 raised to the 3x minus 1 equals log of 10. It allows me to pull the power to the front. You're going to divide by log of 2. So you have log of 10 over log of 2 equals 3x minus 1. So try that. So log of 10 divided by log of 2. I get 3.322. So I'm keeping that in my calculator. I'm adding 1 to it, and I'm dividing by 3. So you should get x equals 1.441. Did you guys all get that? Okay, good. Okay, so we had one on your homework, like in 10.1 or 10.2. That looks kind of like this. It says, suppose a bacteria culture doubles in size every hour. How many hours will it take for the number of bacteria to exceed 1 million if you start with 1? So we're still thinking of it like this. And we started with 1 bacteria, 1 bacterium. And our rate of growth ends up being 100%. Do you remember that from the homework? A lot of you guys asked me questions about that. Because we want it to be just 2 to the t. So if you think about it, at time 0, if you plug in 0, you get 1. At time 1 hour, you get 2. At time 2 hours, you get 4, and then 8, and then 16. It works out how you want it to work. Does that make sense, why it's set up like that? So the question is, how do we get 1 million bacteria? How long does it take? It's kind of gross. It's like this bacteria. What kind of bacteria is this? Is this like the germs you guys leave on the desks? Ew. You're like grossed out now, aren't you? All right, so we have 1 million equals 2 to the t. And we now know how to solve this. We have a variable as an exponent. Whenever that happens, we need logarithms. So we can either switch forms or we can do the log of both sides, whatever you want to do. So let's say this time we switch forms. Then it would be log base 2 of 1 million equals t. So we're going to do log of 1 million divided by log of 2. So what do we get? 19 point, did you guys do it? I think it's like 19 point something 32, 932? 0.329, give me 3 decimals. 329? Okay, thank you. Hours. So a little bit more than 19 hours for it to reach 1 million. Okay, so that's how you do all of the exponential equation ones. Pretty straightforward. Feeling comfortable with it? I know logarithms are weird at first when you first see them. All right, now the logarithmic equations I think are even easier. They're not that bad. Okay, so it says an equation with a logarithmic expression that contains a variable. Okay, like exponential equations, if you can get it into the form log base b of x equals log base b of y, then you can say, oh, x and y have to be the same thing. X equals y. Okay, so this first example, we can't get it to be log base 6 of what equals log base 6 of what, okay? It's already set up. There's not 2 logs on different sides. You actually could get them to be equal, but. Okay, so I don't have 2 logs on each side, so what am I going to do? 6 to the negative 1 equals 2x minus 1. I switch forms. And this is the way that you guys seem to like. You like to switch from log to exponential. It's harder going from exponential to log, isn't it? Okay, so I have 6 to the negative 1. That's 1/6 equals 2x minus 1. You could take 1/6, you can add 1 to it and get 7/6. And divide by 2, you get 7 over 12. But some of you guys seem more comfortable with cross multiplication. So 1 equals 6 times 2x minus 1. So 1 equals 12x minus 6. So 7 equals 12x. So x equals 7 over 12. So what about the next one? What do I need to do? I have a log minus a log. Yeah, so you're going to combine with division. Remember, if you have two logs and you need to combine them into one, if there's a minus in between, we use a division. If there's a plus in between, we use multiplication. It's kind of like our rules of exponents. So I have 4 to the 1 equals 100 over x plus 1. Some of you are super smart in this class. You know the answer already. Because you're like, oh, 100 divided by some number gives me 4. That number has to be 25, so what would I need for x then? 24. You see it? Not 3. So, but some of you guys don't like to do it, like you like to see all the algebra stuff. So that's fine. So you're going to multiply the x plus 1 over here, or cross multiply. So you get 4x plus 4 equals 100. You subtract the 4, you get 96. And divide, and you get 24. Good job. I just said the answer, though. All right, number 3. I might ask something like this in the non-calculator test. Okay, many of you would think to go this route. You would say, oh, I'm going to have 5 to the 6th equals x cubed. And then you'd be like, ooh, what's 5 to the 6th? Oh, I have to do this without a calculator. This is terrible. Okay, you can make it easier on yourself. I know, I see a lot of scrunched faces. So how about this? I have a power, right? I can bring powers to the front. So I can do 3 times log base 5 of x equals 6. And then I divide by 3. So I get log base 5 of x equals 2. Now it's really easy to do. 5 to the 2 is equal to x. So x is equal to 25. Really easy to do without a calculator, right? So what if you had done it, this part, 5 to the 6 equals x cubed? Could you still get the same answer, even working without a calculator? Sure. Just don't do the 5 to the 6. Think of it as the cube root, right? The cube root of 5 to the 6th. So you're going to get 5 to the 6th raised to the 1/3 equals x. Well, what is that when you do 5 to the 6th raised to the 1/3? It's 5 to the 2nd, right? 6 over 3, 2. So you get x equals 24, or 25, I mean. Same thing. Yeah, Alex?
Okay, so I just translate out
Mm-hmm. Yep, that's basically what I did. I raised it to the 1/3. Divide by 3. All right, here we go. Next one. This is the easy one. We love these. What do I do?
To multiply.
Multiply. There's an equal sign in between them. All you do is x minus 10 equals 3x plus 7. Okay, basically what's happening here, so you can write that, but basically what's happening is it's like I'm saying 13 raised to this whole side equals 13 raised to this whole side, and that cancels, right? So we have x minus 10 equals 3x plus 7. Subtract your x over, I get 2x. Subtract the 7 over, I get negative 17. So I get x equals negative 8.5. But there's something wrong with this one.
no solution.
It's right here, right? When you plug in negative 8.5, you get a negative. And log base 13 of negative 18.5, right, doesn't work. It's negative. You can't take a log of a negative. So this is a no solution. I did negative 8.5 minus 10.
But you wrote negative 8.
Yeah, which is negative 18.5, right?
What?
So I'm plugging in negative 8.5 here.
Oh! I understand.
I could tell. All right, next up. So I can't just get rid of my logs on this one, so I have to combine. I'm going to use division. So I'm going to have log base 4 of x minus 10 over 64 equals 2. I do 4 to the 2 equals x minus 10 over 64. So I get 16 equals x minus 10 over 64. So when I do 16 times 64, I get 1024. So 1024 equals x minus 10. So I get x equals 1034. Does that one work? Do I get a negative? No, so I'm good. Yeah. All right, and then this one, if I have plus, Abby, what do I do?
Multiply!
That's right, we multiply. So I get log base 12 of x times x plus 1 equals 1. So I have 12 to the 1 equals, or sorry, maybe I should simplify first. So I'm going to have log base 12 of x squared plus x equals 1. So I switch forms. 12 to the 1 equals x squared plus x. I get everything on one side. You guys are still having trouble with this on the test. It's an x squared and an x. Get everything on one side, and we're going to factor. So it factors into x minus 3, x plus 4. So we get two answers. We get x equals 3, and we get x equals negative 4. So Yaya's saying no solution. Which one's no solution?
No, that was baseball.
One of them is no solution.
Yeah.
Negative 4 doesn't work, right?
Yeah.
But 3 is a solution, so there is a solution. Oh, I'm sorry. I thought it was Yaya. I got confused. All right.
Well, no, you were saying no solution, but I want to say, wouldn't it be 3, not negative 4?
Oh, you were on top of it. All right. So the last little bit. Sometimes we have inequalities. When we have inequalities, we need to use critical values. So whenever you have a less than or a greater than or whatever, you're probably going to have a number line, and you're going to have to test in each location, right? So that's what we're going to do here. We use critical values. Okay, so I'm going to say 2x equals 4 to the x minus 1. I set them equal to each other. And this is one where we can get them to be the same base, right? 4 is 2 squared. So I have 2 to the x equals 2 to the 2 raised to the x minus 1. So I'm going to have 2 to the x equals 2 to the 2x minus 2. So I can say, oh, well, that means that my powers are equal to each other. So I have x equals 2x minus 2. Subtract my 2x over. Did I make a mistake somewhere? Oh, no, I'm good. Negative x equals negative 2, so I get x equals 2. So I put this on my number line. This is the only critical value I have. 2 is what made them equal, so I don't include 2. Because it just said greater than. It didn't say greater than or equal to. But I need to test some points, right? So I'm going to test something on the left of 2. I'm going to test 1. So I have 2 to the 1. Is that greater than 4 to the 0? 2 is greater than 1. Is that true? Yep. How about 3? If I do 2 to the 3, is that greater than 4 to the 2? 8 is greater than 16. Nope. So my side that's shaded is the left side. So my solution is going to be negative infinity to 2. So for exponential equations, you only get whatever critical values you had from setting it equal to each other. For logarithmic equations, we can't have a negative or a 0 here. Like, we can't take the log of a negative number or 0. So we also need to say, well, when is x minus 2 positive? When is it greater than 0? For all x values that are greater than 2. That's where your first critical value comes from this part right here. The second critical value comes from setting it equal. So we're going to do log base 4 of x minus 2 is equal to 3. So we have 4 to the 3 is 64 equals x minus 2. So I get 66 equals x. So it's okay if you had forgotten to do greater than 4, or greater than 2, I mean. Just put it on a number line and test each location. You're testing whether they're true or false. If you try 1, it doesn't work. You can't do the log of negative 1. Okay, it doesn't work. Nothing on the left side is going to work. Okay, it ends up, it's going to be in here. You can test 67 in the original. If you do 67 minus 2, and you're seeing if it's less than or equal to 3, it works out to be like 3.01 or 3.001, I can't remember. And that doesn't work. But if you try anything in here, it does work. So then the very last thing, 66 is closed, but 2 is open because you couldn't have the log of 0. So that's your interval. I'm going to end this so I can pass out your homework. Where is it? Hang on.